of the continuity equation. So what to derive the continuity equation, what generally we'll assume is that, so let us take a control volume which is fixed in the space as you have done in your earlier courses. So of some arbitrary shape and size of a control volume, right, which we will take it. And generally what is our conservative form of the equation is that the net flow out of the mass. So what is the net rate of flow of mass from the control surface is equivalent to the time rate of decrease in the mass inside the control volume. So the what is the basic equations we are applying here in this one is conservation of mass, that is net rate of outflow of the mass from the control volume through the surface S is equal to the time rate of change of decrease of mass inside the control volume, right? No, make a note of this statement or understand this point. Net rate of outflow of mass from the control volume through surface is equal to time rate of decrease of mass inside the control volume. So then what exactly the net mass flow inside the control volume through that surface is, that we have already cleared in the previous session. So that is the density into what exactly this V represents here. Vn, that's a normal component in this one, it is representing. So here it is representing, that's a density into what exactly the density into here in this. What exactly this V represents and this V, what is the difference between the equation one, what is the Vn and V represents here in this. So we are just balancing that particular flow rate here in this one. So just similar to our previous expression of rho AV. So this previous expression of similar to the rho AV. So I'm expressing that the net outflow of the mass from the control volume can be written as rho Vn ds, where in the other side, where on the one side it is complete flow rate is being considered, where the normal component is being considered for the V, but on the other side when we see the vectorial notation, so that is the V is considered in all the three directions, so that is Vh, Vy and Vz, right? So now, so that net mass flow rate of the control volume can be written it as simply, that is m dot is equal to rho AV, right? Density into area into the volume, density into area into the velocity, density into the area into velocity. But here in this point, if you notice, so what we have to understand from this one is, so whatever the equation we have, so we have it on the right hand side, this V can be having a positive or negative direction depending upon the flow inlet and the outlet. This depends upon the flow inlet and the outlet. But always this ds bar represents the conventional direction pointing outwards only. Always the ds represents the positive outward direction only, right? Whereas we can represent the negative direction or the positive direction depending upon the flow inlet and the outlet. Depending upon the flow inlet and the outlet, the velocity can vary, but the net resultant flow which is coming out through the surface is outwards only, which we have discussed even in the earlier sessions also. So then the resultant of V dot ds can be positive or negative. So that depends upon the problem you are approaching. Right. So the net resultant of a ds is positive always, but the V velocity depends when it is multiplied with the V dot ds. So the net product of this one, so that exactly defines the direction of the velocity which is being accounted there. That defines exactly the velocity which is being accounted here in this one. So let us write this total mass flow inside the control volume. Let us write the total mass flow inside the control volume as the mass is generally rho AV, right? So rho AV, area into the velocity. So where it is varying with respect to the time. So here what we have written is density inside the control volume is rho into the dV. So what exactly this dV is actually the V bar. This V is actually the V bar. So that means the velocity in all the directions. So that the variation of the velocity in all the three directions. So that mass. So where you have taken a triple integral means it is taking the complete control volume. So mass inside the control volume is represented as density into the volume. Or from your simple definition of the density, I have brought this equation 2 here. So what exactly the simple definition is? Density is defined as mass per unit volume. Density is defined as mass per unit volume. So here my interest is what is the mass inside the control volume. So that I have written it as mass is equal to density into the volume overall the integral of this integral, that is a triple integral, that's the volume integral of the flow. Now the question comes, why the volume integral has come into the picture here? Because whatever we are considering it as a small control volume, so when I'd like to apply it here to the entire control volume, for that reason I've taken it as a triple integral of the volume. So that this volume need to be accounted in this particular flow. So the total mass inside the fluid flow is that is a volumetric integral of rho into the volume. So that is that volume I have written in terms of the velocity. That volume only I have written in terms of the velocity, right? So that is being written as rho into d, right? Now, when I'm interested to talk about what is the net variation of the control volume to correct that particular equation in the previous term, so it is being representing that rho into dV, but it should be actually the density into the volume to address that particular equation. So what we have done is that whatever the rate of change mass inside the control volume, whatever the rate of change mass inside the control volume is taken as dou by dou t of, that is volumetric integral of rho dV. So the volumetric integral of rho dV, right? So here in this equation, the conservation of mass can now be written as, dou by dou t of whatever the change in the volume happening inside that, whatever the change of volume happening inside that particular fluid flow, plus the surface integral of rho v dot ds, which is being taken from your yesterday's discussion, that is the divergence theorem. So surface integral of rho v dot ds, this total term need to be going for the 0, that is the equation 4. Or when the fluid flow is involved within a complete fluid flow, that we can even write it as d by dt of rho dv. d by dt of rho dv is equal to 0. Then we can say that the conservation of mass, or mass is being conserved. The mass is being conserved. So the resulting equation that results in the equation 5. That results in the equation. So this in the previous slide we have seen from the equation 2 to the 5. So that is about the how mass inside the control volume is balancing out. So and finally the resulting equation that is written in the substantial derivative d by dt of rho dv, so which represents the equation 5. So here we can see that the different forms of the continuity equation earlier we have done with all courses. So here what are the equation derived in the equation 5? Here we can see that the dou by dou t, so that is the variation with respect to the time. So that is rho dv. Rho dv, that's the volumetric change is happening inside this fluid flow, and this I told you that bold v will be representing this velocity here in this. So v dot ds. So this equation 1 represents integral form of the conservative integral form of the continuity equation, where fixed control volume and fixed in space, where it is having the fixed control volume and it is being fixed into the space. And if you see on the second part of it, the integral form of the equation which is in the non-conservative form. So the change which we notice it from the conservative form to the non-conservative form is, so here the total equation of the integral form of the equation has been written equivalent, that is d by dt of triple integral of volume into rho dv. So that is only volumetric change is being addressed here in this one equation. So that means here we are related with this volumetric change of the fluid flow. So now you may question it how this equation can be equivalent to this one. So as the path A says, the conservative and non-conservative forms both represent the same form of the continuity equation. How it is being addressed in that equation is, here the volume, so that is the change in the volume which is addressed here in this equation, that it is varying with respect to the time is one, and the change in the volume happening in all the direction, that is vx, vy and vz, so that is xyz direction, the volumetric change. So but here we are addressing with respect to the variable of the volume, that made it to discuss as in a non-conservative form of equation. And in the conservative form of the equations, we have taken separately the velocity into the surface change, and we have discussed that the density into the volume, right? So from the basic equations, from the integral form of the conservative and the non-conservative form, both the equations represents the same. So that means there is no change, or if you have written this in the conservative form or non-conservative form, both the equations would be utilized in our computational fluid dynamics. But not only this path 1 and 2, but we have already, or you might have already done in your previous courses, that path 1 is same as path 3. So what exactly this path 3 is representing is, where we have considered these two approaches are within a finite control volume, FCV's approach, but this is an IFE, infinite control volume approach. So infinitesimally small element, so that is a finite element approach. So when we are considering the elemental approach here, if you see, so where in this one, so the d rho by dt, where in this one, so the d rho by dt, so that is the density variation with respect to the time, and the complete it is being written as curl of a gradient, curl of a velocity, that is delta into delta dot rho v, bold v represents the velocity. This is in the differential form of the conservative equation, where infinitesimal small element fixed in space. And here if you see, infinitesimal small fluid element moving with space, moving with the flow, right? So in that case, my total equation of the partial derivative of the conservative form has formed into the differential format. It has formed into the differential format. Okay, so this has become path. Here on the screen we can see that the differential form of the conservative equations and the differential form of the non-conservative equations, where in the conservative form of equation we have the partial derivative with respect to that variable alone, but in the differential in the non-conservative along that particular with respect to the time variation. Similarly, when we are talking about the integral form of the conservative forms in the fixed control volumes and in the mass moving with the control volume, right? So that is infinitesimal and the finite control volumes and the moving control volumes. So where is the one common point we can notice is in non-conservative form the equations are being addressed within a total derivatives, and in the conservative form the equations are being addressed within a partial derivatives. So that means along with the fluid flow, so that is being addressed on the equations with the partial derivatives for the conservative and non-conservative form for the differential derivative, right? Differential direct total derivative, right? So this is what we have noticed. So whenever we are saying that it's a partial derivative of the fluid flow, so that means we are interested along the path of the fluid flow and we are very specific to that particular point or the direction of the fluid flow, then only we are approaching to the conservative form of equation. So in computational fluid dynamics, all the equations or any equations would be utilized for us. So like this the equations are, so we'll be utilizing any equation for our equations to solve it, so that we can approach to the any way in this particular one. So this represents the different forms of the different forms of the continuity equation, that is a fixed control volumes with a fixed space and moving with a moving space also, with a fixed in space and moving with the space also, right? So this is what exactly about the continuity equations in the equations or the derivatives of the continuity equation in a simple way. We are going for the continuity equation in a simple way derivation. We are going to achieve it, right? So we are going to obtain this continuity equation derivation in a simple format. So let us go for the continuity equation derivation in a simple way. How do we, so for to derive this continuity equation, so just in the previous slide we have concluded that either in the conservative form or the non-conservative form, the total continuity equation can be, any continuity equation can be utilized in our analysis or theoretical or the applications. So for that one, what I have considered is, I have considered an infinitesimally small, control volume, which in the x direction which is having a distance of dx, and in the y direction which is having a distance of dy, and in the z direction it is having a distance of dz. As you can see on the screen, dx, dy and dz. So these are placed on the rectangular quadrant where the velocity vectors along that particular direction are given by I, j and k, that is along the x, y, z direction. So on this I have kept a small infinitesimal small fluid element fixed in space. Remember this point, that I have fixed this small element which is fixed in space. Now, so my control volume is fixed. So that means I am infinitesimal small control volume fixed in space, right? So if you like to see with the comparison with the previous approach, so here you can see fixed control volume fixed in space. So that is the first form I am going with. So, but here it is the infinitesimally small, so that it is infinitesimal. Derive the continuity equation for it, right? So as the control volume is fixed, as you can see on the screen here in this one, as you can see on the screen. So as the fluid, let us take that the fluid is entering from all the three directions. So as the control volume is fixed, the fluid can enter in all the three directions. So the fluid which has entered in the direction of the x, as we can compare on the above, as we can compare in the above one. So the fluid which is entering, the mass flow which is entering it from one side and leaving out on the other side. So that is in this direction. So in this space, the fluid is entering. On this surface, the fluid is entering and leaving out on this face. Okay. So that is what about the fluid is entering in one direction and leaving out. So that means entered from one face and leaving out from the other face. Okay. The fluid has entered and leaving out from the other face. So when the fluid has entered from one direction and leaving out on the other direction, so leaving out from the other direction, so what is the change we are supposed to notice? So as we are considering it as in the directional wise, as we are considering here it is in the directional wise, what we have done is, so the directional velocity, so the direction in which the velocity is moving, so that is along the u direction. The velocity is moving along the u direction. This is moving in the direction of u. Okay, so this is moving, the velocity is in the along the x direction, we have represented with the u, and y direction we have represented with the v, and z direction we have represented with the w. So when it is moving along the x direction, that I have written it as density into the velocity into what exactly this dy and dz has come. So this dy and dz is our area. So how you have written this equation? Next question comes, how you have written this equation? You can't bring it from the space directly. As the control volume is fixed in space, we can't bring it directly from the space. So how I have written is, have written based upon the formula of mass flow rate. So that is rho into area into the velocity. So this is actually from where I have brought that equation. So that means the mass flow rate which is entering into that one. So that is density into the area into the velocity. Now the next question comes. So what exactly is the density along this fluid flow? So we have assumed that the density along this particular fluid flow, or for the fluid the density is rho. For the fluid the density is rho, and velocity along the direction is u. Velocity along the direction is u, and the area, because since it is covering which one in this one, so this is covering this face. So that face area is actually dy into the dz, right? Yes. So that is actually dy into the dz. So that is the face which is being moving out from here. So this is the face which is moving out, entered from that one and moving out of this. So for that reason, this dy and dz are being multiplied, are being taken as an area. Since it is moving along the x direction, so that it is the x velocity. This one, so that is now. So when it has entered from one end, when it has entered from one side and leaving out on the other side, so that means when the fluid is leaving out on the other side, will there be any change happening in the fluid flow, or the fluid will be moving with the same velocity? That's the question rises next. So but if it is in real fluid, if it is a real fluid, definitely there is a change is going to happen in the velocity of the fluid flow. So to address that thing, so whenever the flow is leaving out, whenever the fluid is entering in this phase and leaving out from the other phase or the surface, what we have written is, so the change has happened. So that is the density, so rho u plus dou of rho u by dou y. So that is dou by dou y. So dou by dou y of rho u into the dx. So what exactly this partial derivative is addressing here in this one, here in this equation is, that is the variation. So here actually it is mistaken. So here it is wrong. That is not dou y. That's actually dou x. It is dou by dou x. So when I am writing the partial derivative into the total derivative, my equation again comes as rho u only. So partial derivative and the total derivative will cancel, and finally I'll get the resultant as dx. Dou by dou y both will get cancelled. So here in this equation, that is dou by dou x. I'm sorry for that. So here it is wrong in this one. So whichever the slide has taken. So that is dou of rho u by dou x, it is actually into dx, into the dx it is actually, right? So this is a mistake here in this one. So plus the change in that direction. So in which direction the velocity is varying? Along the x direction, because I'm considering we are talking about this x direction fluid flow. So that x direction fluid flow where the change has happened, that is in the direction of the x. So dx and this dou by dou x will get cancelled, and finally our equation resulted with the entry and the exit will remain same. Okay. Oh, fine. So that when we are addressing this, equation, so this is what the change happened in the fluid flow. This is what the change happened in the fluid flow. So rho u dy dz plus rho u dou by dou x of rho u into dx into dy into dz. Right. Similarly, if we write in the other directions, in the y direction and in the z direction, we are going to get the same equations, but here in the velocity direction, that is y direction, that is rho v dx dz, rho v plus dou by dou y of rho v. In the z direction, it is rho w plus dou by dou z of rho w into dz into dx into dz, dx into dy. This is what we have in the total expression of the continuity equation, where the fluid is entering and leaving out as the control volume is fixed and it is infinitesimally small fluid element we have been considering. If anyone is interested, can make a note of, if you are interested, can have a look in this one. So what exactly the fluid flow is coming out in the all the three directions of the fluid flow. So individually in the partial derivative, we have addressed this. We have addressed this one, right? Okay. If we see the net flow resulting in the x direction, the net flow resulting in the x direction when we are resulting from the, when it is entering from your left hand side to the right hand side, when the fluid is entering and leaving out, so the net flow in the x direction is resulting in the equation of rho u dou by dou x into dx dy dz minus rho u dy dz. Okay, so here the resultant equation in the x direction and the y direction, and finally when we write the net mass flow rate resulting from that equation is, so here you can see net mass flow in the x direction and in the y direction and in the z directions. So here our terms of the equations here, rho u d by dz is got cancelled. So finally we are left with dou by dou x of rho u dx dy dz, rho v dx dz in the y direction, in the z direction. So this we have totally in the continuity, this we have totally in the directions of the fluid flow. But the net resultant is actually, it is totally infinitesimal control volume, infinitesimally control volume. So that is being fixed into the space. So that the resultant is a summation of all the three directions we have resulted in that one. So finally the net mass flow out of this control volume is, that is dou by dou x of rho u, dou by dou y of rho v, dou by dou z of rho w into dx dy dz, which I have taken all the three equations, that has resulted in the net mass flow out of the control volume. Right. So what we can see is the volume of the fluid element is dx dy dz, and the mass of the fluid element can be written as rho into dx dy dz. So that the time rate of mass increment is dou by dou t of dx dy dz. So our equation of net outflow from the control volume is equivalent to the time rate of decrease of mass within the control volume. Since we have mentioned that is the time rate of mass with the decrement in the control volume, that need to be represented within a negative sign. That is minus dou rho by dou t dx dy dz. So finally our equation is turned as, finally our equation of the continuity we have obtained it as dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z, where the density is accounting with respect to the time variation, and here the density is varying along each direction of the fluid flow, and it is along the derivatives, the partial derivative along all the directions of the fluid flow. So this equation is in the conservative form. This equation is available in the conservative form, as we are addressing that it is in the partial derivative equations. This is in the partial derivative form of the equation. So this is giving the conservative form of the equations in the continuity equation in the conservative form. Okay, so which becomes, we can finally write our equation like this. So in the slide number 61, which can be written as dou by dou t of del dot rho v is equal to 0. This is a continuity equation which is valid even for the unsteady flows. Which is valid even for the unsteady flows. In case of the steady flows, simply we can cancel out this dou rho by dou t as a time variation. With respect to the time variation, density will not vary. In case of the steady flow, dou rho by dou t is equal to 0. So this is our equation which we have derived in this session now about the continuity equation in the conservative form. Continuity equation in the conservative form. And finally, let us conclude it here about the continuity equation which we have discussed earlier, so that the different forms of the continuity equation can be obtained. So just now we have obtained this equation of the continuity, so that is in the path 1 and path 2. So that is the path A and path C. Both we have done in this one, and this is what we have brought it in the differential form of the continuity equation. So initially we were talking about this one, and finally we have ended up over in the differential form, the conservative equations. So that is the continuity equation in the differential forms. And here in this one there is a small change you have to notice in that one is, so there is a correction need to be made. So there is a correction is required in this slide or the image. So the correction is actually here in this. So the correction is, here it is being represented as a P, but it's not actually P, it's actually the rho. It's actually the rho which has in the differential form of the equation can be written in that. Right. So with this we conclude that the continuity equation is derived in the conservative and the non-conservative